In this video, we're going to talk about concavity in graphs. So let's just make sure we all know what concave up and concave down mean. So concave up generally looks something like this. Or you can also imagine sort of splitting it in half. This is also concave up just by itself, right? Or this is also concave up just by itself. And concave down is sort of the opposite of these things, right? So like this is concave down, this is concave down, this is concave down. So when you're looking at curves, curves of graphs, like these types of pieces would be considered concave down, these types of pieces would be considered concave up. Okay, well, but we don't want to just like pass the eye test. We want some algebraic way of sort of like capturing this concept. So let's see what we get. The definition here, if f is differentiable on an open interval, then it's concave up if the derivative is increasing, and concave down if the derivative is decreasing. So let's go back up and look here. You can see, remember the first derivative represents like slopes of tangent lines, and if I think about them, they start out negative and they get like up to 0, and then they start getting bigger and bigger and bigger, and you can see in each of these cases the derivative is increasing. And even here it looks like maybe that wouldn't be increasing, but it starts out super negative, right? And then it's sort of approaching 0. So in all of these the derivative is increasing as you read left to right, and all of these the derivative is decreasing left to right. Okay, so it turns out that's the algebraic concept that we want. Turns out there's this theorem that says if the second derivative exists on your open interval, then if the second derivative is positive, your graph is concave up, and if the second derivative is negative, your graph is concave down. And that makes a good amount of sense. If you remember, how do you tell when a graph is increasing or decreasing? You look at its derivative, right? And when the derivative for the graph is positive, it's increasing. When the derivative is negative, it's decreasing. But what's the derivative of the first derivative? The second derivative. So when the second derivative is positive, that should mean that the first derivative is increasing. But of course, when the first derivative is increasing, that's the definition of concave up, right? And the sort of a similar sort of train of thought follows for negativity and decreasing. Okay, so note, a change in concavity happens at what's called an inflection point, or a point of inflection. So this is sort of harder to see. Like we know where like critical numbers happen, right? So like critical numbers are a first derivative phenomena, and they're when the first derivative is 0 or undefined. So you can sort of see them easily in terms of like a top of a hill or the bottom of a valley. Inflection points are a little bit harder to see. They are where a graph changes from concave up to concave down. Okay, so you can see here I've kind of emphasized this point is all sort of concave down, and then somewhere in here, right, it kind of shifts. And then over here now it's concave up. So these are sort of harder to spot than critical numbers if you're just looking at a graph. But a point of inflection is called, or it's called a point of inflection when your graph changes from concave up to concave down, or vice versa, right? Concave down to concave up. One comment though, this is not a point of inflection. A point of inflection has to actually be in the domain of the original function. So if I look at this, and this is my original function, this is concave up and this is concave down, so I did switch from concave up to concave down, but I did it at a discontinuity in the graph. So that doesn't count. We don't call those points of inflection. All right, so again, we don't want to necessarily just rely on looking at a graph. We want some sort of algebraic way to capture a point of inflection, and we have it. So this theorem says that if your function is continuous and you take a point in the interval, if the second derivative is 0 or the second derivative doesn't exist, and the second derivative changes sign, then that is an inflection point, basically. So a comment about this is a lot like critical numbers. If you know what critical numbers are, they're where the first derivative is 0 or doesn't exist. And that's sort of what this says, right? Like where the second derivative is 0 or doesn't exist. However, the first derivative, when you're talking about critical numbers, you don't have this extra and condition. So that's why I've sort of like got it in capital and underlined here. You've got this extra condition when you're talking about inflection points. So let's just go ahead and work one of these. So find the points of inflection and the intervals of concavity, meaning where is it concave up and where is it concave down, for the following function. So if you want the points of inflection, remember that is where the theorem we just saw said that's where the second derivative is 0 or doesn't exist, and it changes sign. So of course if we want the inflection points, or if we want to talk about concavity, we're going to need the first first derivative so that we can get the second derivative. So just power rule here. First derivative is 15x to the fourth minus 20x cubed, and then second derivative, again, power rule. I'm not choosing anything crazy here for the functions just because I'm trying to exemplify the concept here. So this will be 60x cubed minus 60x squared. So again, if you go back and look at that theorem, if you're trying to identify points of inflection, or if you're trying to figure out where the intervals of concavity are, right, that's sort of like, those are going to be demarcated by the points of inflection. So I need to know, where is this not exist? Well, none of those. This is polynomial, but you can end up with, variables in the denominator or whatever. So there are ways for this not to exist, or like if you have trig functions, for example. So really what we're going to think about is, when is this equal to 0? So I can factor a 60x squared out of this and leave myself an x minus 1. And then if I sort of come over, right, the 60x squared, using the 0 factor rule here, 60x squared equals 0, x minus 1 equals 0. So this is going to give me 0, this is going to give me 1. Now, if I were asking myself about critical numbers, and that's, remember, the critical numbers is a first derivative phenomenon, these would be critical numbers if I was sort of doing that type of problem, but because we're talking about inflection points, I have to do an extra test. I have to make sure that the second derivative actually changes sign around these things. So what I do is I take these two potential, right, so these are my potential candidates, potential points of inflection, and I'm going to sort of graph them on a number line. So that's a kind of crummy number line, but you get the gist. So this is 0, this is 1. And I know, since these are the only places where the second derivative is equal to 0, that in between, in all of these intervals, right, so I've got the interval here from negative infinity to 0, the interval from 0 to 1, and the interval from 1 to infinity. And I know that within any of these intervals, the second derivative behaves similarly, right? So if there's a single point in here where the second derivative is negative, then it's all negative here, because it would have to cross through 0 to become positive, but I know that these are the only places where it hits 0. Similarly, if I test over here and I get something positive, right, then everything over here is positive for the second derivative. Because again, if it wanted to change to where the second derivative was negative, it would have to cross through 0 first, but that only happens in these places. So what I do is I just take some representatives. Let me just choose a different color here. So I take some representatives, maybe say, I recommend choosing numbers that are easy to work with, so perhaps negative 1, 1/2, and 2. You just take any representative numbers you want, you throw them into a table, and see what they give you. So let me get back my black pen. So I take these things, and I'm going to plug in these representative numbers. And then the question is, where am I going to plug them in, right? Am I going to plug them into the original? Am I going to plug them in the first derivative? Am I going to plug them in the second derivative? I'm going to plug them into the second derivative, because what I'm interested in here is whether or not the second derivative actually changes sign. So I'm going to use this sort of factored form of the second derivative here. So when I plug in negative 1, this is going to be positive times negative, right? So I don't actually care what that number is, but I do care that this is negative. I plug in 1/2, this is positive, and this is negative, right? So that's going to be positive times negative is also negative. When I plug in 2, this is positive and this is positive, so the net result is positive. And again, I don't care what the actual value is here. I'm just checking to see if it changes sign. So now I've got everything I need to answer both the original questions. So points of inflection. Remember, the original question asked for any points of inflection, but also asked for the intervals of concavity. And I can answer all of that based on the work on the screen. So concave up, concave down. So before I talk about the answer, you may want to just pause and ask yourself, based on this work, what is the answer? Okay, so remember, points of inflection, that's where the second derivative is equal to 0 or undefined. So we had these two candidates, 0 and 1. These are our potential ones. And then if I go and look, around 0, right, I ended up with negative in this interval, negative in this interval. That means this is not a point of inflection, right? This is not a sign change. Scrap, right? 0 is not a point of inflection. However, this is a sign change. So I'll have a point of inflection at 1, and then f of 1, whatever that is. I mean, you can plug that in and see what it is. But yeah, this will be a point of inflection because I did, in fact, get a sign change around the second derivative. And then if I want to think about the intervals where it's concave up and concave down, well, that's essentially what all these signs are telling me. These are my sort of intervals where concavity is acting similarly. So because I got a negative, that means that the graph is concave down on this interval. So, for example, concave down, negative infinity to 0. And then you can use like a union symbol or maybe just a comma, depending on how you write your answers here. But 0, 1 is also going to be concave down. Don't make the mistake of slapping these intervals together. Okay, this thing is not concave down from negative infinity to 1 because it is neither concave up nor concave down at 0. Okay, so don't make the mistake of thinking that just because these act the same you can smash them together. Don't. Keep these intervals separate no matter what. And then of course, right, this one was positive out here, so that's where we're going to be concave up. So this is the answer to the question that was asked. And that's just a sort of primer on graph concavity, points of inflection, which sort of demarcate the intervals of concavity, and how you can think about the shapes of curves using the second derivative.